Velocity-controlled performance with a fingertip-controlled admittance-type haptic device. To control an admittance-type robotic device, a human interacts directly with a force sensor mounted to the robot, and the robot is computer-controlled to move in response to the applied force. Admittance-type robotic devices are commonly used to complete tasks that require a high degree of precision and accuracy, in part because they contain a great deal of gearing and inertia such that they are non-backdrivable. The University of Utah Active Handrest is an example of an admittance-type device. It is a handrest that moves intuitively to support the user's hand and enable fine motor control within a larger workspace than otherwise would be possible. The Johns Hopkins University Steady Hand Robot is another admittance-type device which operates on a precise scale not attainable by humans by effectively reducing the tremor in the operator's hand. This video summarizes research that was conducted to determine under which operating conditions humans most effectively control admittance-type devices with the fingertip. The study was conducted using the setup shown here. The subjects interacted with an admittance-type robotic device while watching a visual feedback display. The admittance-type device moves on a lead screw-driven linear stage that is actuated with a DC motor. The force sensor is mounted on the moving portion of the device. The subject interacted with an admittance-type device by applying a force on the force sensor. A visual display showed a colored sphere that indicated the position and velocity of the admittance-type device, as well as a stream of white squares that moved at a predetermined constant velocity. The sphere shows yellow when the device is ready to begin a trial. When the subject applies a force, the sphere turns green and the trial begins. The sphere turns red when the trial is over. The subject's goal was to match the velocity of the admittance-type device with the desired velocity. This was accomplished by matching the velocity of the colored sphere with the velocity of the stream of squares. Once a trial was finished, the device was reset and the sensor recalibrated in preparation for the next trial. The results of this study show that there exists a range of velocities and forces within which humans optimally interact with admittance-type devices. To maximize velocity control accuracy, the optimal range of velocities is between 0.4 and 1 millimeters per second, and the optimal range of forces is between 0.4 and 4 newtons. To maximize velocity control precision, the optimal range of velocities is also between 0.4 and 1 millimeters per second, and the optimal range of forces is between 0.4 and 10 newtons. This shows that velocity control accuracy degrades at higher force levels, and good precision can be maintained through a larger range of force levels. In this case, both the desired velocity and the target force were within their respective optimal ranges. After a short ramp-up period, the subject was capable of consistently matching the desired velocity. This study showed that changing the visual velocity scale factor only had an effect on velocity control performance for very slow velocities. When the desired velocity and the target force are within their respective optimal ranges, velocity control performance was unaffected by the scale factor. If the admittance gain is set such that the target force becomes too high, velocity control accuracy is poor. In this sequence, the target force was set too high. Subjects had poor accuracy because they had the tendency to lag behind the desired velocity. The amount of effort required to attain a high target force is apparent when observing the strain on the subject's hand. Velocity control performance is poor if either the target force or the desired velocity are not within their optimal ranges. Although it does not take much strength, it is as difficult to consistently apply a very small force as it is to apply a large force, especially when the desired velocity is very slow. This sequence shows very poor velocity tracking. When the target force or the desired velocity is too small, humans are not capable of performing manipulation tasks precisely or accurately. When an admittance-type device is used to enhance human manipulation performance, the workspace is essentially enlarged to a size that is optimal for human performance. Likewise, the velocities and forces can be scaled such that humans can perform manipulation tasks accurately and precisely. This research shows that the admittance gain should be selected such that the manipulation velocities and forces are within their optimal ranges.